Yeah.
Next in the series of seminars on advanced transportation technology sponsored by the Roadway Safety Institute. I'm Max Donath, and today we're going to have Professor Bill Schneider speaking. Before he begins, I just wanted to say that this seminar is broadcast over the internet. So all of you who are not located here in the seminar room, what you should be seeing on your screen on UM Connect is on the upper right-hand corner. There's a bubble which you should be clicking and then type in your name and affiliation. All of you have questions. If you're not here in the seminar room, please type them into the window which is just below the place that you click on the upper right-hand corner. Anybody here in the room needs to use a microphone to ask questions. Otherwise, nobody in TV land or World Wide Web land will hear what you have to say. So please keep your questions to the end so that we don't have to spend a lot of time moving a microphone all over the place. Anyway, without further ado, I just want to introduce our speaker. He's an associate professor of civil engineering at the University of Akron. The University of Akron is one of our partner institutions, part of the Roadway Safety Institute, which is a regional university transportation center. Bill Schneider has been working in the area of transportation for a long time in air quality, ITS data management, and the impact of geometric design on safety and operations. You'll learn a lot more about his research from his seminar. Before he joined the University of Akron, he received his PhD at Purdue in 2003, spent 2 years at the Texas Transportation Institute, and then ended up at the University of Akron. I also know that he is a well-qualified plumber and electrician, so if any of you have any home repairs and you need someone to do them, he's the man. Anyway, without further ado, Professor Schneider.
Thank you very much for allowing me to talk today. So a little bit more about my background as we go through. I do a lot of work, too, in the safety world. That's part of the reason why we're joining on this UTC. One of the areas in particular interest for me is looking at alcohol-related crashes. The reason why I got involved in this is a few years ago. I was at a sobriety checkpoint. I had a colleague at the Department of Public Safety that said, hey, would you like to go see what one of these things look like? And I said, sure. I had no idea what they were. And so we went out to this checkpoint, and we pulled this person over, and she had 3 kids in the car, and she was about 35, 38. The youngest kid was maybe a year old, and she fell out of the car. She couldn't even stand because that's how drunk she was. And I just said at that time, I was like, wow, this is really it hit me for the first time that this is a serious thing, and I wanted to do something about it. One of the other interesting things is, as a professor, you talk to a lot of students, and traditionally speaking, the most likely student or person to get an OVI or a DUI, depending on your state, is the person coming right out of college. So there's it's a big group for a lot of reasons. So today we're going to kind of mix a few things. We're going to talk a little bit about alcohol. We're also going to talk about the mapping and some of the modeling that we're doing to make this stuff go. A couple of things here in terms of crash costs of life. 237 lives were lost in the U.S. in the last 20 years. 6,000 in the state of Ohio since 2000. Almost 1,200 children under the age of 14 were killed. And you can kind of see this, just like most safety-related events, you can come up with some statistics that are pretty scary, if you will. So these are some of the original things that we looked at. Other things that we talked about this morning and other times that you'll see is what's the cost of a fatal? You know, and there's a lot of debate, and it's really interesting if you look across the world what other countries use as different cost ratings. So in the U.S., it's somewhere around $3.5 million per fatal, and which results in about $42 billion lost nationally as a result of this. Other things that we looked at is you know, since this is a basic class, I want to give a couple just, hey, here's a little snapshot of the problem before we get into some of the modeling. Drunk driving analysis nationally, different days of the week from 2010 to 2012. And not surprising, you see, hey, it's the weekend. The Sunday, is typically, hey, that's 2 o'clock in the morning. That's probably more related to the Saturday driver than the Sunday driver. But again, you can see some of that. Below, we have an extra year of data, but you can still see that same general trend. So what are we showing here? We're saying that basically state of Ohio is not substantially different than what you see nationally in terms of some of the overall data in terms of, okay, which day of the week do you go and things of that sort to do enforcement. Other things that we have there, the top graph there is national, the bottom graph is Ohio. The y-axis is the number of fatals. X-axis is time of day. The 99 at the end is an unknown value. So again, we're not splitting the atom here in terms of when and at what time are a lot of these fatal crashes happening. Interestingly enough, when you start looking at impairment, one of the new trends is looking at prescription medications and lower doses of alcohol that can create impairment. You may not be at 0.08, but you can get up quickly and be impaired. So these are some things that we're also starting to look at in terms of research. Other things that we wanted to give you, again, some other backgrounds on is look at the difference between seatbelt use between impaired operators and non-impaired operators in crashes. In the top, 91% of the crashes involving non-impaired operators had a seatbelt on. You go down to the bottom one, it's 65%. And so not only are you drinking and driving, but you're also not wearing a seatbelt. So there's a, you know, it just is a compounding effect, if you will, in terms of what kind of message are you going to send to people about these different things. So how does this then relate to what we do? One of the things that I've recently been involved at is I run an OVI task force, which you would call here as a DUI. Task force in the state of Ohio. So I manage, or my group manages, anywhere between 15 and 18 different agencies at a time. And our goal is we, as the university, provide them with crash locations, contributing factors, information of that sort. And then the law enforcement guys go out and they do different enforcement strategies to determine and to help prevent crashes. And then the third prong that we do is the educational side of linking these bad habits with driving. The other thing is as we look at this, we're going to go into mapping, is what a good portion of today's conversation is going to be about. And the reason for that mapping is we want to be able to say, hey, this is where crash is occurring. Local law enforcement person, this is where you need to be prevalent and be well aware. Education, if you're going to spend a little bit of money, this is the best place to spend your money to get the most bang for your buck, if you will. So when we look at this, we have basically a twofold approach. And this is taken off of DDAX, which was a NHTSA initiative, which basically is saying, hey, you guys collect a lot of data. Use the data to help improve your overall program. This is, in essence, what that is. And so what we're looking at is the current, is the information for courtrooms, education, law enforcement. What we call here is driving for dollars. and that is to say, hey, sure, you could put a law enforcement officer on the road, but if they're on the wrong road, what's the point? And then the second one there is what we're looking for is, the future, the long-term budgeting. How do you manage different resource allocation? Because we're supposed to, in today's economy, do more with less. So how do we make all that stuff work? And then ultimately, the final is you want to come up with some sort of non-biased way that you could say, this is why we're here instead of somewhere else. So a good chunk of the rest of this presentation is going to talk about, some different strategies that people have done over the last 20 years or so on mapping crashes, and then where are we going? And it's very interesting. I went out to lunch today, and we had on one side of the table is very theoretical. This is what's going on. And on the other side of the table, we had a very applied, and it was interesting to see how the two can get glued together on some work. What I want to talk about here is this is just this is the crashes. So this is the state of Ohio. I guess I can, up there's Cleveland, Akron's about here. You can see that's Columbus, Dayton, Cincinnati. So, you can almost pick out the population densities based on where a lot of the crashes are happening. But similar to a lot of projects now, and, a lot of you people are grad students, so you collect data. So that's the first part. So you collect the data. Now, what do you do with the data? And what you'll find out is what you do with the data may be different than what this person does and that person. And there's strengths and weaknesses to all sorts of ways of analyzing data. There is no one, this is the correct way. And so when you look at this, okay, this is 2009 to 13, these are the crashes. Where's your crash problem? And so this is where we wanted to start talking about some of the data. So then what we did is I just went back into some of the literature and I focused predominantly on crashes. So I'm not talking about what's happening in other areas, just how have we used some of this technology with crash-related mapping. And so one of the papers that we see that's quoted or cited fairly regularly was this one from Kim and Levine in '96. And basically what they did is they broke it down and said, hey, we've got 3 different ways that we want to look at crashes. One's the point-based, saw it on the last map. The second one is a segment-based, so here's my road, where do I want to look? Third is a zonal-based, so how do we define zonal? Are we looking at a county? Are we looking at a city? Are we looking at a 1 by 1 mile block? What exactly are we looking at? And each of these, they each produce different explanations of studied data, and they all have pros and cons to them. It's a good way to do it. And so let's kind of just dive into some basic mapping that you'd see. So you've got 2 maps here. The one on the far left is a map that we used that the Ohio State Patrol did for Stark County, which is where we run our OVI task force. Again, it's a point-based map. And you're basing it just on where's the location of the crash. Second one there, it gives is from a paper, and it basically gives a couple things that you're looking for. One is you look for the mean center of the area, and then you develop some sort of standard deviation or distance around that map. So you could just say, hey, here's where the center is, and one of the things that you might want to look at is what you see here. Does that move? And if so, by how much? And one of the things, and that's what you see on the left side, is think about that as from a geospatial point of view. Maybe just call it an XY axis, and where is that center moving over time? And one of the things that there's a big debate in enforcement. If this is my problem spot, and I put a lot of police officers in that one spot, The problem's going to go somewhere. The problem could either A, go away, and you fixed it, or problem B, you've pushed it to someplace else. And so one of the things that they could say is well, okay, where you are, that's fine, but now we've moved crashes to a different area. And so one of the things that we're looking for there is how much does it move. The second one on the right is starting to look at clustering, if you will, of the crashes using z-scores to see if there's any statistical significance about these particular areas. And so you could look at and say, well, the reds are close together, the yellows are a little bit further out, and so forth. It's almost a temperature map. Reds bad, blues not necessarily your problem. And again, as we talked about before, and throughout this, there are multiple ways of looking at this data. A second way that you could look at it is a segment-based. And we've got two examples of the segment-based maps. The one over here is an interesting way of looking at it, because if you think about it, the tools that I have in the state of Ohio from an enforcement perspective is I can tell law enforcement agencies, drive on this road. You're only allowed to drive on this road. And the second one is hey, that's called corridor enforcement. The second one that I can do is I can say, let's do saturation patrol. And that basically says, hey, you law enforcement officer, you can drive, but you got to stay within this boundary. And so as we were talking about at lunch today, which one's the better way of doing it? Okay? And so the way we looked at it, or a way to think about it, is the top one over there is measuring all around. So it's not just on that road, it's the roads next to it, it's the parking lots, it's the driveways. And so if you're talking saturation, that's a good idea. It gives the law enforcement officer some flexibility while staying within the boundaries of the field. The other way of looking at it is based on network distance. And so what's nice about that is I can say, hey, this is my justification for you staying on this road. Don't leave this road. This is what the data says. Because at the end of the day, at least in Ohio, you have to be able to validate or verify that you are enforcing or educating in areas that actually have problems. So that's an important thing that we look at. The one on the right here, you can see different levels of gray, and basically you're saying, okay, here's my problem spot, here's a first order and second order. And so what you're doing is it's a very classic hierarchy. You can do it in a couple ways, whether it's GIS or a hierarchical Bayes model using a negative binomial model. You could do something like that. You'd say, I know that these other areas influence this particular spot. I don't know exactly what it is. And so sometimes you look at that and say, we can use this because I can't collect all the data. And when you guys do your research projects, you're not going to be able to collect all the data. Okay, so it's a way that people have gone around it. But again, you're looking at other ways of potentially modeling. One of the challenges that we see from an enforcement point of view is they say, okay, here's one road, there's a crash over there, there's a series of crashes over here. So you can go on these two portions of that road, but then what do you do here? Am I allowed to be in this area, or do I only have to be here? And what about the cars that actually drive both ways? Okay? So those are some things that we've looked at there. Again, some other ones that you could look at. Benefits, you're looking at distances and things of that. One of the challenges, and again, it depends on your definition of challenges, and is, if you zone out, do things get lost? If I zone out at the segment-based level for the entire state, and you've got, a couple thousand segments of road, where do I look? It's that resolution going up or down, or at least in the area that I work in. So those are some things that you would consider. Okay. So then the next one that they do, and you can use all of these together, and you can pull the strengths and weaknesses out of these, is a zonal-based way of looking at this. And again, what you're doing is you're drawing your field of play and you're saying, okay, within this area, what am I looking at? One that's very common right now is census tract data. You get, we don't have to collect that. U.S. Census data is available. You just get that layer for GIS. Boom, it's in there. It's a justification. A lot of people, especially safety-wise, will look at rural versus urban and different things like that. So those are some things that you could look at. Also, you could look at counties, traffic analysis zones. So if anyone in here is doing origin destination studies, planning studies, they do a lot with that data and say, okay, how does that go across? Other ones that you could do is again, and similar, let me start again. A lot of times what you'll do with this data is you'll look at where is the center of that zone, because that is what we're going to call, we're going to see if things move. And how far is this center from that center, that center, that center, and that center. So those are some things that we're going to look at. Over on the right is the classic example that you'll see in terms of changing the colors based on county. So you can say, okay, well, we just swapped the whole state. You could probably figure out, where the urban areas of Michigan are and look at that and say, okay, we can target the money there. We can help do some of that. One of the challenges that I'm currently still struggling with is how do you normalize out for big population centers? Because when you talk about alcohol crashes, the city of Cleveland will have a lot of alcohol crashes because there are a lot of people that live in the city of Cleveland. So, at the end of the day, when you look back and you do a lot of high-level modeling, they say, well, yeah, we know that Cleveland has a problem, or we know Columbus has a problem. So those are some higher-level issues that you would think about. Positives provides analysis of an entire study area. Negatives, one of the big negatives is it's an arbitrary boundary. It's a county line. It's so you can potentially make things bigger or more significant or less significant based on how you draw your box that you want to look at. Pro is, okay, I know this county. This is where it is. And again, we looked at two different things. This one on the right, we took to the next level. This is the most advanced modeling that the state is doing. Sorry, I better not say that. This is one of the new techniques that the state is doing, which is defining them as grids. So we're going to take the county, we're going to make it even smaller. So when you look at it, these areas in red are areas that we seem to have more problems than others. Okay? And so that's a grid base, which is even more fine in terms of how you want to look at the particular data that you have in question. So in addition to this, what I'm looking at is there's still a lot of work that's being done in these areas, so don't necessarily get hung up in terms of past, present, and future, because the various aspects of these people are working in. What we like to look at is, okay, so if you look at the past stuff, you have the point-based, you still have the segment, and then basically, and then the zonal, and then basically all these different methods are used to identify relations between each other. That's the goal. So there's strengths and weaknesses to them all. As you look at it here, so we just highlighted a few that we've seen reproduced in the literature. And again, when I say literature, for the most part, we're looking at just crash-based literature. We're not talking about geography or computer science or other statistical journals. We're trying to keep it in. So the top one there is average nearest neighbor. And then the clustering is based on the distance of each point to the nearest neighbor. So you think about the red dot in the middle. That's a crash. And the blue dots or the blue-gray dots around the outside are other crashes. And so it goes from that crash to all the other crashes. And then we go to the next point and do that. And then we go to the next point and do that. And from that, you come up with this average nearest neighbor. Okay, so that's one way. And what are we trying to do? We're starting to figure out how do we how do we glue all these crashes in together? The next one that you're going to look at is the Getis-Ord, or the general G or GI star. And basically what we're doing is and the corresponding, an example of that is we're trying to do figures next to them so you can kind of see this is what the words say, this is what the map looks like at the end. Basically what it's doing is it's identifying concentrations that are high or low or medium and medium or high and medium, things of that sort. The high and low values, and identifies the G identifies concentrations throughout the study, and the GI star again identifies the high or low values. So again, Cleveland, Akron, Columbus, Dayton, Cincinnati. And you just look at that. So that's the way you want to look at it. Another way that people have looked at it is the Moran's I at the bottom. And basically what that does is it identifies if neighboring features contain similar or dissimilar values. So it's saying, okay, this is what mine are. Are we close to next to them, or are we not close to next to them? And then what does that mean? And so you kind of, this is from a paper in 2009. You can kind of see the difference there in terms of how these look. And then at a global, again, the entire area, and then you could do local in terms of adjunct areas that you're looking at. So what I want to look at here is let's start breaking this down in terms of, this is sort of a structure that we at Akron have started looking at. We are relatively new to the mapping game. The reason why we're doing it is because we had a lot of law enforcement guys through our task force that have said we need a tool that we could justify why we are where we are. And so that's where we started looking at this. So for about the last year to two, maybe three, we've been in this field. So let's go through the steps here. So the first step that we're going to look at, benefits of the new analysis, and then we'll kind of step through and show some of the data. So the way we want to look at this is sort of a this is a point based. This is all the exact same data that we're looking at here. So this is alcohol crashes, all the exact same data, and you can see how we go from the point, the zonal, to the current in terms of this. And basically, you see the benefits of both the point and zonal. You can analyze them all through the current study area. And one of the things that we looked at the end, it removes the ambiguous zonal borders. So there's a difference between the three on how we're going to model what that is. And so that was one of the things. And then it's interesting at the bottom, you can say there's a shift in significant areas maybe seen between the zonal and the current analysis, looking at the same data. And again, that could be based on how tight things are. It's still in the same area, shifted down slightly, but you still are picking up the downtown Cleveland area, as well as over here. This is as you go across. So you still see some of the highs and lows associated with it. And then what we're going to do is sorry, let's step back. So this is where we're going. So we're going to go, how did we get to the current? Possible methods used that you could look at. So we looked at kernel density estimation, and it's basically the density of crashes within a specific bandwidth. So how close are those crashes? Then we're going to look at the values, again, are in crashes per unit area. And then density values range from 0 to high, however you want to define that. So this is one of the first ways that we look at it. And we got two examples right below and one to the right of some ways that people have looked at this bandwidth, if you will, over time. Second one down below is a cluster and an interpolation. And it calculates the statistical significance of crash clusters. So we started to want to look into, is there significance to it, or is it a random assessment? one of the things that you're going to look at if you ever do work in safety is there's a huge underreporting of single vehicle crashes in rural areas. And so you'd say, well, what does that mean? Well, if you've been drinking all day and you drive off the road and you hit a small tree but your car is relatively okay, you might just hop back in the car and keep on driving. Or if you take out a mailbox or you turf a yard, it's not uncommon for that to happen. So was there a crash there? Yeah. Was it reported? No. And so that's a very common thing that you will see that's relatively well documented across the safety world is how do you handle these crashes that don't exist. Down below, again, you're looking for where are your areas of significance in terms of how you want to define them. What we looked at here is how do you define sort of spatial autocorrelation between different groups? And so the ways that we looked at is we looked at global Moran's eye over a study area. And basically, it identifies the presence of spatial clustering. It returns an I-value and a z-score. So basically what it says, the I-value indicates the type of clustering, and the z-score is either going to reject or accept that the data is randomly distributed. So is there reason for the data to be there, or is there reason for it not to be there? It's basically what you're looking for. And then you go down below and you say that the GI star is there to determine, again, if clustering is present. So when you look at it, you see a GI score. So the higher the score, the more significance there is that there are clusters, or in the case if it's real negative, there aren't clusters. So, as we talked about to lunch today, and I didn't even really think about it until lunchtime, was, well, what's the point of looking at the areas with no data? Or sorry, with no crash clustering. So that's something that I want to take back. Once you look at that, you can look at it at a global level or a local level there. And basically, you're looking at the local GI star, which is each feature. And basically, it identifies features of clustering for high-frequency crashes. And again, it still returns a z-score. So again, the significant positive cluster or significant negative. So you see here, again, same data set, Cleveland versus some other areas where there are more significant and aren't. And what we're trying to do is say, is there a correlation there? I guess one of the things that we could look at is if there aren't any crashes, is there something unique geographically to that area that would encourage them not to be? Is there a high presence of law enforcement? Is there 0 bars? Is there 0 people living there? In Ohio, and I could probably make some arguments, in Ohio we have Holmes County, which has a very huge Amish population. So very low vehicle travel, a lot of horse and buggy. So again, is the population density unique? Other ways that you could look at it in terms of spatial autocorrelation is looking at your cluster interpolation, if you will. And so what we're looking for here is it basically, you want to distribute significance of the clustering throughout the entire study. And that we've looked at the interpolation of it. So if it's red here and it's red here, what's going on basically between them is what we're looking at there. So, and what's nice about that is so you remove the boundary of the county or the block, however you want to do it. So you're trying to see what that grid is. So we've looked at a couple of ways of looking at it versus deterministic or stochastic, exact versus inexact, and then coming down below in terms of, so one of the things that we looked at, we've been looking at kriging of the data set. So is a stochastic and it's an exact interpolator. And it calculates an assessment of the prediction errors, and we'll get to that here in a few minutes. and then it predicts a value at each point that is the same as the known. So basically what you're able to do is you're able to go from the point base, which is your far left, showing clusters that are significant, and now it's trying to relate those clusters of significance to other clusters of significance or other clusters of insignificance, I guess would be the way to look at it. And so what you're seeing here are three different ways. Now we talked about it at lunch, and I was thinking about this. The discussion at lunch was right now we're treating this as a continuous hotspot zone. Okay? Is there a way to say, well, do we really care about the whole hotspot, or do we just looking at the max spot within that hotspot? And so after lunch, I was thinking about what we've done to this date, and again, I'm not saying that this is right or wrong. This is just where we're at. Is we looked at, it's easier to see over here, everything on this side of the line. We thought it had a z-score greater basically than the 1.96, so we said 95.5% confidence level. That whole group would be considered the main target area, if you will. Or at least that's the way that we looked at it. The second one, or the last one over here, is we're looking at different prediction errors. And so we're trying to predict based on what the interpolator says of areas where there's more separation, variability in the data. So the darker the color, the more variable, less prediction that we can do. We come down here to some other ones. So the next thing is basically how do we create the models is what we want to do. And so basically we want to be able to identify the variance between the crash locations and a model representing the variances and trends. And so it's kind of hard because there's a lot of moving parts that go on the same point, but we wanted to kind of show spatially what's behind the scenes here, if you will. So we did a Kriging interpolation, and my guess is there's probably dozens of different interpolation methods, and they have different strengths and weaknesses. We're, again, relatively new. This is what we are focusing in on right now. Throughout the remainder of the study, we may change, but right now this is it. And basically what we looked at it is we looked at its interpolated values are calculated from the weighted value of each cluster location, and that the weights are determined from the average semivariance and the semi-variogram model. And so what you want to look at is so you've got individual data points in here, and the way that I like to think about this is very similar to what I would call if you've taken a regression class, or Excel. You plot your points in Excel, you hit the trend line comes across. And so what we're trying to do here is we're looking at the individual average semivariance points, which again are right here, identifies the difference in z-scores for two clustered locations. So here's crash cluster 1, here's crash cluster 2. What is that average semi? So those would be the individual data points. The versus distance. Okay, so how far apart are we looking at those different groups have scores. And so what you're going to do is based on these individual points, you can plot a semi-variogram model, which is basically to represent the trend in the semivariance. So if you think about this as a regression or Excel, you've plotted your points, you hit the trend line, it says y equals x plus 10. That's in essence what we're doing here is we're trying to say, okay, what is this? What does this mean? And then what we're going back to is that you can also, the way I it's not 100% right, but it's the way I look at it. The further that distance is, that also goes back into the the darker values here. Okay. So other things that you want to look at is okay, where does this go in terms of your spatial, your model estimation and testing? So this would be sort of a next phase that you would do that would help complete to say, okay, is this model right or not? As you guys go through model building statistically, you'll find that model building is not a exact science. There is some interpolation along the way. There's different methods that can be used. And so these are some ways that you want to look at it. So when we did the Kriging, we compare semi-variogram models through cross-validating the data using a drop one or leave one out technique. So fitting them and then re-comparing them, see what's going on. And then basically, it removes 1 point from the data set, and then it re-estimates it with that data set, with that point missing, and starts looking to see how that makes sense. And then basically from that, you can go and it calculates the predicted error, again, by comparing the estimated value with the original removed value. So you could look here in terms of, these are your benchmarks there. Your mean, an optimum value would be 0, centered. Your root mean square error, you want to get that as small as possible. You have a standardized mean, you'd want to get that again as close to 0 as you can. Standardized root mean square of maybe 1. And then again, you want to average your standard error. You want to minimize that as much as possible. And so what we're looking at here is the best semi-variogram model is determined as the one that basically reduces the most error. So there's multiple different techniques that you could do to look at that. And that's one of the things as this our UTC project goes through, this is one of the things that we're looking at. In terms of future spatial work, and again, when I want to make sure I reiterate this, future to me is what our group's doing. Some groups may have been doing this for a while. Basically, what we want to look at there is we want to see that there's continued improvements that can be made for how you do your clustering. And again, you want to be able to make sure that you can increase your accuracy. And you want to be able to make sure that you get your contributing factors correctly. I mean, so that's a key step that you want to look at. And so things that we're looking at Akron that to improve it is we want to look at improving the spatial interpolation through both the multivariate interpolation and improved model estimation. And we also want to look at the improved cluster identification using a multivariate cluster identification is where we're seeing some of that stuff or that work being done. And so what does that mean? It means you can basically look at your data this way. And so in a multivariate interpolation, you want to use different data sets. So think about it this way. One data set is your crash locations. One data set could be U.S. Census data, or it could be, where are we giving tickets, or where, so there's different levels that you can look at that you can see. And you want to look at the correlation. And what we're talking about here is this cross correlation between the two data sets is based on the two separate locations. So think about this is where the crashes are occurring. And the second layer above that, is this where the tickets are? Or are the tickets on the same spot? Or is the U.S. Census data on the same spot? And is there or is there not? And that's what you want to look at that bottom is sort of looking at that correlation versus distance. And the correlation is a data point with crashes versus your other attributing layers of census data, time of day, or things of that sort that you could look at. And then again, the cross correlation between the two data sets is based on the separation distance between the mean centers of both sets of data. Another one that we're looking at here is improved model estimation. So I showed you that blue line before and I said, remember, it's like a regression model. basically what we're saying is we could split that data up a lot of times, and we could do simulation of that data set. And one of the ones that you'll see is people are using Bayes analysis on that. So basically with a Bayes analysis, you're saying, I know a little bit about what it should be. And if I know a little bit about what it should be, then I can do a better job on the prediction by basically saying, if I know a lot about what it should be, that values that predict close to that, I'm going to make stronger than values that are not what it should be. Okay? And so that's one thing that we're starting to look at is how can we simulate this and stream this to really fit that semi-variogram model, if you will. And this is just sort of a general picture of looking at that over a lot of simulations. And then again, interpolated values are still going to be based on weighted sums of these semi-variograms. And then the weights are based on the distances from the prediction location. So again, similar to what we did before, but oversampling and seeing if we can refine it. Another one that we're looking into is can we do some sort of multivariate cluster identification? Great example of that is let's say you were looking at pedestrian crashes. It seems like that's a very popular topic in Minnesota, pedestrian crashes. Well, if you looked at it geospatially, one of the things that you could do is you say, well, hey, University of Minnesota's campus, we have, and I'm just making up numbers, there was 20 ped crashes last year. It's a really high number in comparison, and everyone's 22 years old, or 20. Then you'd say, well, okay, if you were an outsider, why would you look at it? And you could start then going into it a little bit more. Well, the University of Minnesota is here. There's a whole lot of people of one particular age group especially that are concentrated right here. It's a unique population. One example. Other things that you could do, and what we looked at here is going back to the main. Here are a lot of crashes. So group B are the red dots. Group A is the blue dots. We only have a few of them. So we're going to look at that. That's that contributing factor. And so that's one way that we feel that we can quasi-model contributing factors associated with human factors in crash models, is a way that we're looking at that. And so what you would see here, this is, again, just a generic way of looking at sort of a, that's a standardized value, and we're looking at distances there for injury severities. So you might say, University of, again, I'm going back to the pedestrian example. You may say, okay, lots of crashes with PEDs. Most of them are not bad because maybe the speed on the roads is relatively slow, or fill in the blank versus another particular spot. That's the kind of level of analysis we're trying to do. Or if you hit something big, you're going to have bigger problems. Some of it, what I like to say on some of this when I teach a statistics classes is when the statistics match the physics, things make sense. And sometimes it gets you in trouble with the sponsor when you're saying, okay, motorcycle crash, motorcyclist was going 140 miles an hour, he's more likely to die. Well, okay, makes sense. Coming over to the last one, this is the other key spot that we're looking at. So the first portion of the lecture, 95%, was how do you build a better map? In essence, is what we're trying to do. Why do we want a better map? Well, a better map allows for, if you have the exact same amount of money, how do I manage my resources? One of the things I always talk to students about all the time is you say, well, what do you mean manage resources? That makes no sense to me. Every student I've ever known, about the time finals week comes along, calculates their grade for every single one of their classes. And they go, going into the final, if I study really, really, really hard, I can get an A. If I don't study at all, I've got my B locked in. I'm only going to study a particular amount of time during exam week. So which way do I maximize my study time? Is a way that I've talked about, managing your resources. Here, how are we managing it? We're managing it from an education and enforcement point of view. Where should the campaigns go out? where should the enforcement details go out? Because again, at the end of the day, instead of the limiting time being how many hours do you have during finals week to study, it's this is how much money we have, this is how many law enforcement officers we have available, or safe communities groups that, again, participate in other ways. Those are sort of the key crux that we're going with. So over the next, or the remainder of this first phase, we are going to identify ways that we can optimize some of our mapping. That's really the first step that we want to do. And we're going to be basing that predominantly on what we've seen in the crash fields. And then from there, we can do a nice sensitivity analysis that says, how does this stuff vary over time? The challenge that we have, I can tell you right now as we move forward, the population density areas, City of Cleveland, they're always going to have a crash problem in comparison to some, if you're looking at just raw numbers, if you don't normalize that data out somehow. So that's one of the things that we're looking at in the future. And again, that's part of our why you guys invited me out here today as part of a Region 5 UTC. And so we're the good state down there in the. And there's the consortium members. And then the last slide here real quick is, this is just a reference of the papers. A lot of the maps that we pulled in here were our data that we used, but a lot of them we pulled from other papers as just some examples of data that's out there, or maps that are out there. So that's all I've got.
Thank you. Any questions? Can't imagine there aren't any questions. How about looking at the effects of laws on DWI and besides enforcement?
It's interesting. We have not done a lot with that with this. We've done more with the effects of laws on motorcycles and helmet use between Michigan and Ohio, looking at that border there of.
And what do the results say?
The results say there are laws that I have to be careful of how I word this one.
Word it any way you like. Nobody's listening.
So the results say that, yeah, that some of the laws, if the laws are done in a correct manner and are properly known and enforced, help. Is the way I would.
What's the correct manner?
So one of the challenges, let me give you a better example. So in the state of Ohio, it's a secondary offense to text and drive. It's a primary offense if you're under the age of 18. So if you're a law enforcement officer, if you're over the age of 18, you can't pull, but basically means, and maybe it's primary and secondary isn't the correct term, but basically what it means is that if you're over the age of 18 and I pull up next to you and I look over and see that you're texting, I cannot pull you over for texting. I can pull you over for speeding, and then if you were texting at the same time, then I could cite you for texting and driving. If you're under 18, it's a primary offense, which means that I could pull you over. Problem is, if I'm a law enforcement officer, I'm driving next to you, not sure how I gauge if you're over the age of 18 or not. And so that's what the law says. And so the enforcement side is trying to figure out how the two go hand in hand. I guess is how I meant to say that before. But that's currently. And then the other thought is because of that, instead of people texting this way, we've now dropped it to text. So you're spending all your time doing this, whereas before you kind of had the. That's what we're seeing.
Here.
So you mentioned the link-based analysis, and and actually, if I look at data type, that seems more natural because all the crashes are on the road. Right? They are not in open space. So if you have a lake next to the road, or open field next to the road, may get colored by the area-based method. So have, what, do you have plans to try link-based methods, and do you see if your results will be any different?
So let's go back. So basically, we're talking about in a pretty simple this. When you cluster this way, your hotspot could include a parking lot, a field, all sorts of things. And so you're 100% right. People are going to say that's no good. The pro to the argument is if you include that, it allows for law enforcement to move off the network a little bit. The other pro to that, and logically speaking, is just because the crash happened here, there's a good chance that it took them a little bit to get to that spot, whether it was on the main road or on a side road. But you're 100% right, and so yes, we are going to look at the link, because the link says, hey, here it is. The con from an enforcement side is you're not allowed to leave that road. You have to stay on that road. And so one of the cons that happens, and this is what we were talking about, the impact of enforcement on crashes. If I'm enforcing this road, what's the first thing that a bar is going to say? Law enforcement's on US 22. And so what does everybody do? They take the back road. So they've shifted over 3 blocks or 10 blocks or a couple routes. So I think that from an enforcement point of view, again, outside the modeling point of view, the combination is really accurate, because you'd say it is good to say law enforcement, you have to maintain a presence here and have a little bit of flexibility. If you give them too much flexibility, you go everywhere.
So one more related question. You brought up bars, and bar closings seem to be correlated with increase in these things around midnight, right? And in fact, your temporal data, if you can bring back your slide where you had crashes by hour of the day, seems to...
Oh, there you go.
Yeah. So you notice around midnight, right, these numbers are higher.
Yep.
When does the bar close in Ohio?
Oh, boy. It's been a long time since I've closed out a bar in Ohio.
So let me broaden.
It's after midnight.
Yeah, okay.
2?
Yeah. So let me broaden this question. And in Lincoln, Nebraska, they actually did this demo. And you can see as soon as bar closes, it's like a bomb going off in the neighborhood. You have misdemeanors, and then you have drunk driving arrest. So are you looking at any temporal analysis? Are you going to look at sequence of what events precede these crashes? Yeah.
And what's interesting in Ohio, one of the lowest days of the year for alcohol crashes is New Year's Eve. And that's because what's the one day of the year that everybody follows? Get a hotel room, get a limo, get your DD. It seems like it's that one night. Versus one of our worst days of the year is the Wednesday before Thanksgiving, because people come back home and they go to the local establishment, meet up with their old friends that they haven't seen in a long time, but yeah, no, the temporal data is definitely there. The new challenge with impairment is the 3 o'clock in the afternoon, which has a blood alcohol lower, is on pain meds and had a beer at lunch. We're starting to see that that's becoming, it's not becoming a massive problem, but it's something that's now starting to get on the radar screen a lot more is the daytime. And so when it comes to our enforcement stuff, we're pretty much bound that we have to do all, because of data like this, after 6 o'clock. And really, we try to encourage everybody to do it after midnight. But yeah, the temporal stuff is huge. I'd be interested to see if there is a weather component. You know, whether it's rain or snow, do people go out and they know that it's snowing?
What's the data like for morning, like on the weekend, for example, on a Saturday morning? So if people went out on a Friday night and the blood alcohol level the morning after going out, is there any data that's on the rise for something like that?
So that's the other one. So we'll call him the power drinker. Your body can metabolize about 1 beer an hour. So where we're seeing secondary OVIs is you went out to the bars, you went somewhere, you slept for 4 or 5 hours, and then you got in your car and you drove. And you're still, because of where you ended the night, you're still above that value the next day. That happens more often than not. But again, what's interesting is if you look at an enforcement detail, most of the enforcement detail, if I went back to the state and said we want to start targeting morning, it would be almost impossible to justify.
Anyway, we're running out of time. There's a lot of interesting data that the Bureau of Criminal Apprehension here in Minnesota captures about DWIs. We were both out there this morning. And the effect on the economy, the tourism industry, the influence of the lobbying industry, the distributors of beer and their influence on local enforcement. There's a lot of interesting parameters that can be explored, and again, using a lot of these GIS methods. Anyway, please join me in thanking our speaker for an interesting talk, and let me also tell you that in 2 weeks, we will have Professor Imran Hai from University of Minnesota Duluth talking about connected vehicles and the technology that they're now examining, exploring for understanding traffic data, and using dynamic short-range communications, DSRC, for communicating data from vehicle to vehicle, vehicle to infrastructure, etc. That's 2 weeks from today on December 4th. Anyway, thank you very much.